Hi, and welcome to the appendix to the third tutorial. I say the appendix because I didn't have a test or a validation or verification at the end of my third tutorial, and I didn't have one conceived, but I thought maybe there should be one, and so I thought of one and I made this one. And so if you're following along where we left off, basically what we're going to do now is we're going to add a test. And the test is just going to be that we want to make sure that our random Gaussian distribution that we're drawing from actually is random and actually is in a Gaussian distribution. And again, if you don't know what those things mean, that's okay. Those are things you can eventually learn. However, all I'm saying is that we want a distribution that looks like a bell curve, and we want to have randomly sampled from that. And so to demonstrate that that's actually what we're doing, I'm going to invoke a new, module called matplotlib, and we're going to plot the distribution that we sample from. And instead of sampling just 10 times for 10 years, we'll do a sample that does 1,000 samples. And so we'll get a very big sample size, and we'll be able to see what kind of distribution we have. So to start off, we'll go to the bottom of our code that we finished previously, and we're just going to make a test bed here. And we're going to print the word test, and now we're going to just import here. We can import at the top, at the bottom. We can import anywhere we want, but we can't use it until we import it. We're going to import matplotlib.pyplot as PLT. And now we're going to make an empty list of annual _ interest rates. Empty list. Okay. Now, what we're going to do is we're going to loop over 1,000 times, and every time we go through the loop, we're going to append to this list a random Gauss sample using the mean and sigma that we invoked in our last tutorial. So inside of a for loop, we're going to say for I in range 1,000 : Now we're inside of a loop, so we need that tab, this 4 spaces over. List of, we'll just copy that, list of annual interest rates dot append, open close parentheses, and inside we want to say random dot Gauss mean comma sigma, and make sure that all of our parentheses are correct there, and all of them appear to be. So that's it. Now we can go back outside of the loop, and we want to plot it. So we've imported this matplotlib.pyplot as PLT, and the easiest way to plot a histogram is plt.hist and the list of values. So we're just going to copy and make sure we paste it right inside there. And if you're lucky, that's all you need. If you can invoke new things, like you can tell it to print or to only plot over a certain range. You can give it bin sizes. We'll add to our complexity of what we know about the plot.hist function here. But for now, we're just going to plot this list, and now we'll say plot.show, and that just brings up the final image that we want to see. All right. Well, everything looks like it's in place, so we're going to hit save, and I'm going to hit this play button to see what happens. All right, so now the plots should show up in this pane up here in something called plots, and if it shows up somewhere else, that may be normal, but this is where it shows up for me in my version of Spider. And so you can see we have this distribution that goes from a little bit less than -10% all the way up as high as almost 30%. It seems to be centered pretty close to 7%, which is our mean value. And so that's what we expected to see. And in fact, if I run it again, I expect now to see a slightly different but similar distribution, right? Because we have 1,000 different samples creating a different histogram plot. And it looks similar, but you can see that these are two different images that were randomly organized by Python using this random.gauss distribution. So here's the verification that we are in fact calling and getting a random distribution. What this distribution means, if you don't understand statistics and histogram plots and whatnot, is that in this case the most likely numbers were in this bin. And this bin goes from, I can't see the edges of it, but it looks like it's about 5% to 8% or so. And then the next most likely bin was this one here, and then these two bins were almost equally likely. And then that's what a Gaussian distribution is, or a bell curve, is that the probability is at the central value, and as you move away from the central value, you have a lower and lower probability of getting those numbers. So that's the kind of distribution we wanted, and that's the kind of distribution we seem to have, and that means that we're getting good numbers in our simulation right now. Good in the sense that they're the numbers we want to get, not good necessarily in the sense that they're correct, but that's what we're going to work on in the next tutorial, where we'll bring in realistic a distribution of numbers from actual market returns for over 100 years of data or so, and given the actual market returns, we can get probabilities or get market rates that mimic actual data. So thanks for sticking around for this appendix to tutorial 3, and I hope to see you in the next one.